So I wanted to start today with an example here. It says, prior to the pandemic, the United States enjoyed almost 8 straight years of economic growth and declining unemployment. In your opinion, who was most responsible for this record low unemployment? And we got 3 choices here. We've got former President Barack Obama, current President Donald Trump, and former pop star, I guess, current pop star, whatever you want to call it, Britney Spears. So think about this. We're talking about like 2012 to 2020, okay, right when the pandemic started. That's when we saw unemployment start to increase once again, but for the preceding 8 years, it had been steadily declining. So who do you think is most responsible for that stretch of low unemployment? Obama, Trump, or Britney Spears? Well, I think I have some compelling evidence that it is Britney Spears. You see, in 2013, this is when she released her song that I kind of have to censor for you right now, not really school appropriate, but Work, Bleep. And right around that time, you can see that the United States unemployment rate went down from about 8%, down and down and down over 2018. It's in like 3%, 2% range around 2018, 2019, right until the pandemic struck. So maybe it's Britney Spears who's getting America off the couch and back to work. Maybe we need a little more Britney Spears to get our unemployment rates back down low. Okay? We see this pretty strong correlation here. Okay? The song comes out, unemployment drops. But we know that this doesn't make sense. Okay? Does correlation indicate causation? No. This is a huge flaw with statistical thinking. And in fact, I have a quote here from a paleontologist and evolutionary biologist that, he was famous enough to guest star on an episode of The Simpsons, but he said, the invalid assumption that correlation implies cause is probably among the 2 or 3 most serious and common errors of human reasoning. We see it all the time. I mentioned it the other day about how it's very tempting to want to infer causation. Okay, I gave you that example about the number of ministers in Pennsylvania and the number of liquor stores. Okay, they are strongly correlated with one another. They both have a positive correlation, but there's no direct relationship between them that one thing is causing the other. So we're going to continue to talk a little bit about correlation and the interpretations today, but also about that linear regression model. Okay, so we have our targets here, analyzing and making predictions using those models, using the residuals to help determine the appropriateness of a linear model, making predictions, interpolations, and extrapolations, and when we can appropriately do that. And lastly, talk a little bit about some of these limitations of correlation. So again, I'm going to kind of move through this because you know what a linear regression model is. It's a line of best fit, essentially, straight line describing how the response variable changes based off of that explanatory variable. I have an example here that is looking at the predicted gain in fat based off of the change in non-exercise activity, NEA change. So you can read about this type of example in your textbook, but what its foundation is about is that people who seem to eat a lot of food, eat a lot of calories, and don't seem to gain any weight, scientists have found that a lot of times they engage in a lot of non-exercise activity. Okay, you could think of like teaching, like me standing up here teaching every day. Like that's kind of a non-exercise activity. It's not directed, focused exercise, but it's movement. It's unintentional. Could be kind of just jitteriness that is keeping the metabolism active and processing some of those calories. So what this is saying is that the more calories, the higher this non-exercise activity, this NEA, the lower the fat gain. And we see that there's a little bit of a relationship here, okay, this negative relationship. So our question asks, what if the NEA change is 400 calories? What is the expected fat gain? Okay. Well, we don't have a point right here at 400 calories, okay, but we could use our model to help make a prediction. Now, some of the algebra and the math behind these linear equations, we know that we're used to this slope-intercept form, y equals mx plus b. And I mentioned this on Wednesday when we went through the technology and how the calculator wants to use this format right here, y equals a plus bx. That's typically what we see in statistics, in that the initial value, the y-intercept, is right here, this a value, while we know that this b value, the slope, is multiplied as the coefficient of x. So our explanatory variable is x, our response variable is y. We know that this y-intercept occurs when the x value is 0. Now sometimes that's a relevant value in our data set. If it makes sense for 0 to be a possible value of the explanatory variable, then that y-intercept, or this a value, has some meaning to the problem. That's your initial value, that's a starting value. But if our x value doesn't range all the way back to 0, then that might not make any sense in the terms of the problem. Slope always has some meaning to the problem. It's a unit rate, okay? It's a rate of change. So you know how to find slope, change in y over change in x, okay? How much does that y value change for every unit of x change? This is talking about plotting the line in the scatter plot. We're typically going to use technology to assist us with that. Now, this line of best fit is really called a least squares regression line. It's the most common linear model that we use. And the way this works, okay, is that the line makes the sum of the squares of the vertical distances of the data points from the line as small as possible. Okay? So what this does is we're calculating the means of x and y, so x bar and y bar, and the standard deviation sx and sy of the variables, and their correlation r. We talked about how to find that r value the other day. Again, I don't really expect you to do this by hand, but we talk a little bit about it because you can gain an appreciation for what's really going on with this set. So when we write a regression equation, we use this y hat value to denote that this is an expected value. It's an anticipated value as opposed to an actual legitimate value. Okay, so we put that little caret on top, we call it y hat. Now, it turns out that that r value does a lot more for us than just define the strength of the correlation and the direction of the correlation. It contributes to another way to find the slope. Okay, one way to find the slope of this line of best fit, this regression line, is by multiplying that correlation coefficient by the standard deviation of the y values and the standard deviation of the x values. Okay? So you know that when we're working with GeoGebra, those are two of the values that are provided. Okay? This is where that slope for the regression line comes from. Okay? It's by taking those individual standard deviations and multiplying by the r value. The intercept comes, you can just do some algebra to rearrange this, and you can find what that y-intercept would be based off of the means. Okay, the y mean minus the slope times the x mean. So, going back to our example problem here, you can make some predictions using this regression line. So, it works out that we have a model here, a regression model, 3.5 minus 0.0034x. So this y bar is the predicted fat gain in kilograms with x calories of non-exercise activity. So to make that prediction of 400, you know you're just substituting it into our equation for x, work it out. We get a predicted value of about 2.1451 kilograms. A little bit of information about this least squares regression. The distinction between explanatory and response variables is essential in the regression. Okay? You need to have x influencing y. Okay? Now this is a little different than what we talked about with the R value. Okay? Remember, R value in the correlation, that does not see the difference between x influencing y or y influencing x. And sometimes that relationship is really reversed. Regression does see the difference. Remember, it's built into that slope equation. And if there was no difference, then standard deviation of y and standard deviation of x would be interchangeable. But that's not true. We need to have this relationship here to calculate that slope. Okay? And it says here there's a close connection between the correlation and the slope of the least squares regression line, and we talked about that slope equation. We know that the slope and the R value always have the same sign. And along the regression line, a change of one standard deviation in x corresponds to a change of R standard deviations in y. That's just based off of what this equation looks like. The least squares regression line always passes through the point x bar comma y bar. Okay, so this can be important to remember, that line of best fit, this regression line, must always pass through the point that is the average of the x's, comma, the average of the y's. That's a good initial point if you were to start to graph some of this stuff by hand. Last one. The square of the correlation is the fraction of the variation in the values of y that is explained by the least squares regression of y on x. So we've seen r squared pop up over our last couple lessons. And we've been focusing on r. The correlation coefficient tells us the form, the strength, and the direction of that correlation. And r squared is just kind of like a byproduct of that. We know that other models use r squared. R is unique to a linear model. Well, r squared has some value for us too. And it goes with determining the variation with our model. Okay, this is an excerpt from the textbook that you could read over a little closer on page 137 if you'd like. But we have our equation, or an equation for r squared. It's the variation in that y model along the regression line as x varies, divided by the total variation in the observed values of y. Okay, so that's kind of difficult to understand and compute. But basically, with our NEA model here, our non-exercise activity, there was an R value of negative 0.7786. So it's a fairly strong negative correlation. We square that, obviously that negative relationship, that number becomes positive. It's a positive 0.6062. We can interpret this as a percent. It means that about 61% of the variation in the fat gained is accounted for by the linear relationship with the change in the NEA. R squared allows you to determine that that percentage, that fraction of the variation is accounted for with the relationship. It's explained by that relationship in that model. On the flip side of that, the complement of that, the other 39%, is individual variation among the subjects that is not explained by the linear model. That's a difficult idea to grasp, and we'll be spending some time throughout the year getting a better understanding about variation and variability. Okay, we know that there is inherent variation built into data. Now, some of that can be explained by our model, Okay, that's what the R-square value does for us. Others, it's just sampling variation. Okay, but R-squared is helpful. The higher that R-square value is, that's telling us the amount of data or the amount of variation that's explained by our model. Okay, if it were a perfect R value of 1, obviously 1 squared is also going to be 1. 100% of our data is explained by that model. Okay, think of it that way as a good way of kind of balancing it out. Now, another way to determine how good a linear model is for our set of data is the residuals. And we took a brief look at the residual plot in GeoGebra on Wednesday. And residuals represent leftover variation in the response after the fitting the regression line. Basically, we said it's the difference between what your value is and what is expected from the linear model. So in this case, a residual is just found by taking your observed value and subtracting away the predicted value. And we're looking at the y's. Remember, we are kind of flattening out our residuals, and we're using our line of best fit as the horizontal x-axis. Okay. So a good way to visualize this is with a residual plot. Okay. The mean of the least squares regression, or the least squares residuals, is always 0. Okay, so you want to look at what's above the mean of 0, what's below that mean of 0. Okay. You're looking for, quote, random scatter around 0. So you want to have the appearance of kind of randomness, an even number above and an even number below, to tell you that this is a good model for this set. So here's the original scatter plot. This is comparing a different example in your book, empathy score versus brain activity. Kind of an odd example if you take a look at it in your book. It was talking about married couples or couples who had been dating for 2 years or more, and if they're married, the husband was subjected to a light shock on their hand or on their wrist, and the wife was then observing this shock. I don't know about the ethics of this experiment. And then her brain activity was tracked to see how much empathy she felt for her husband while he was undergoing this shock. So we see this original scatter plot here with a regression line drawn. And here's the residual plot for that. We see we're flattening out that regression line to become the new axis, and we have some that are above and some that are below. And this appears somewhat randomly. We do have a value here that's kind of away from the rest of our data set. Okay? It's consistent with the regression line. Okay? It's got a high x value, a high y value, and it fits pretty nicely right there. But we have a lot of variation on the lower end of this data set. Here are a couple other residual plots. Like, this is the type of residual plot that you want to see to verify that a linear model would be a good fit. Okay? Even number above, even number below. It's dispersed pretty randomly. It's not like all of our upper values are on the low end and all of our small negative values are on the further right end. Okay, it's dispersed rather randomly throughout. If you get a residual plot like this, this tells you that a linear model is not a good fit. You see this distinct curve here telling you that there's going to be some other model that would be a better representation of this data set. This last residual plot, you might initially think it's similar to our first one, that we have values above and values below, but look at where the variation occurs. Okay? In this case, starting out with our low x values, everything is very compact right around the line of best fit. But then as x increases, that's when we get more and more variability. So thinking about what that scatter plot might look like, this might be a model where it starts out kind of linear, kind of flat, but then starts to shoot up very quickly, like some exponential model might be, or the right side of a parabola for a quadratic model. Okay, so you want that even disbursement across the entire set to make it a good linear model. And this is not the only thing that you're using. You're using this in conjunction with the R value to help you make the decision about the appropriateness of the linear model. Now, we talked a lot about outliers earlier this week and their effect on correlation. Now, sometimes those aren't actually outliers, but they're very influential on the impact that they have on the data set. Okay, some influential observations. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Okay, so we can see that sometimes, that if you are justified in removing some value, then there's quite a dramatic shift in what's happening with that correlation or with the linear model itself. The result of a statistical calculation may be of little practical use if it depends strongly on a few influential observations. So, like, if these influential values are like the crux of your argument and everything kind of depends on those values being there, then it kind of brings into question the legitimacy of that relationship as a whole. Specifically about outliers, points that are outliers in either the x or the y direction of a scatter plot are often influential for the correlation. Points that are outliers in the x direction are often influential for the least squares regression line. We talked about consistent versus inconsistent outliers the other day. Remember, if it's consistent, it fits with the rest of that regression model, and it's going to strengthen that correlation. Maybe that's a good thing. Maybe that's an artificial strengthening. If it's inconsistent, like if you have this trend of increasing correlation, or increasing slope, I should say, and there's an outlier or an influential point that has a relatively low x value and high y value, that's not typical with the rest of the data set. And that's going to weaken your correlation. It's inconsistent. This is kind of looking at outliers and influential points. Here's that last point that we had talked about that had a very high empathy score, very high brain activity. It was consistent with our model. Okay, so it did kind of strengthen our correlation. But when you're looking at the R-square values, remember, after removing that observation right here, the R-square value is 33.1%, meaning that only 33% of our variation can be explained by this model. But if we do have this value present here, our R-square value is now 51.5%, meaning that more than half of our variation is now explained by that model. That's a big swing just based off of the presence or the absence of a single data point. That's an influential value. Okay, so you're going to see more of that when you have a relatively small sample size like this. I think 16 is our sample size in this example. But you get this big swing and it kind of stands alone away from the rest of the set. Okay, so this is an indicator that that's an influential value, whether it's an official outlier or not. We need to be careful about drawing any conclusions and if this model is appropriate for that situation. Have some cautions about correlation and regression. Okay? Some of these we've already talked a little bit about. A couple of these are new. Correlation and regression lines describe only linear relationships. Okay? Don't bring back some algebra 2 ideas or FST ideas about quadratic regression or exponential regression. Okay? Yeah, it's essentially the same thing, and you have an R-square value for those models, but it's not the same thing that we're doing right here. Correlation and least squares regression lines are not resistant. Okay? They're very susceptible to outliers. We talked about that the other day. Here's a new term here for you. It says beware of ecological correlation, or correlation based on the averages rather than the individuals. I kind of fall guilty to this a little bit myself sometimes, that there's a lot of variation based off of individual values. To get an idea about what's happening overall, and if you have a legitimate correlation, you'd like to see data sets and models that are built from the individuals. You have to be careful if you're looking at like X values that are averages, like a state average SAT score we saw the other day, or average graduation rate or something like that. Because with the averages, you have less and less variation built into those just by nature. I mean, they're averages. So everything is going to kind of congregate closer to the mean, and those means are all going to be relatively closer together. So with that being said, if you have less variability when you're working with means, then correlation is usually going to be stronger if you're building a model that's based off of means as opposed to individual values. Okay? That idea is called ecological correlation. So that might mean that you see a correlation that looks pretty strong, but it's kind of artificially strong because you're not looking at a sample of individuals. Instead, you're looking at an average across the entire sample. Beware of extrapolation, predicting outside of the range of X. I talked about this the other day. Okay, if you have a regression model that's built with X values ranging from here to here, it's best used to make predictions with data from here to here. You have to be very careful about extrapolating far beyond that range from which the model was built. If you are to use your model within that original data set, that's called an interpolation. If you're going beyond the range of that original data set, it's called an extrapolation. It's extra. Interpolations are usually pretty good because those are the X values from which the model was built. Extrapolations you need to be careful with. We also talked about lurking variables. These have an important effect on the relationship among the variables in a study, but they're not included in the study. It's not the explanatory variable. It's not the response variable. Okay? You have some third variable in the background that's explaining that relationship, that's more directly influencing both X and Y. And lastly, correlation does not imply causation. Okay? That's the overall arching idea here that you need to watch out for. I have a link here to a website. It hasn't been updated in years. It's called Spurious Correlations. And this guy just compiled a bunch of like arbitrary X and Y values and relates them to each other. It's kind of funny, some of these relationships that you see here. This is looking at U.S. spending on science, space, and technology. It correlates very strongly with suicides by hanging, strangulation, and suffocation. Who would have thought? Number of people who drowned by falling into a pool correlates pretty nicely. Look at this, up and down, with the films that Nicolas Cage appeared in over 1999 to 2009. Per capita cheese consumption correlates strongly with the number of people who died by becoming tangled in their bed sheets. Yeah, that's a vicious way to go. The divorce rate in Maine correlates with per capita consumption of margarine. Age of Miss America correlates with murders due to steam. steam, hot vapors, and hot objects. So, I mean, some of these things, I don't think there's any sort of causation. I don't know what the lurking variable is, but it's kind of like comedic in the way these things are correlated very strongly with one another. We have an example here of a girl who, her age range is posted here from 30 months old to 65 months old, and her age is plotted against her height in centimeters. And we could create a regression model. We see a pretty good linear connection right here. We could use this model to predict her height at an age of 42 months. Okay, go up here, go over there to the y-axis. We can make a pretty good prediction, probably about 87 and a half centimeters tall. Could we use this model to predict her height at age 30? Which, you do the math, that's 360 months. Well, that's an extrapolation far beyond the range from which this data set was built. Right? Just because we see a strong linear model here doesn't mean that it's going to continue like that far into the future. And maybe we could predict for like 66, 70 months, 72 months, something like that. But the fact of the matter is that human beings grow the most their first few years of life. Okay? If we were to continue this out for 30 years old, here's our model. It works out that she would be about 210 centimeters, which means this is a big girl. She's going to be 6 feet, 10 and a half inches tall at age 30 and continuing to grow. You have to be careful with extrapolations. Okay? They might be appropriate just outside the range from which that data set was built, but you know that this growth rate is going to level off. Okay? Being aware of lurking variables. Okay? I have a little example here. The Kalamazoo, Michigan Symphony once advertised a Mozart for Minors program with this statement. Okay, question: which students scored 51 points higher in verbal skills and 39 points higher in math? The answer: students who had experience in music. Well, they say you could just as well answer students who played soccer, because children that have an upbringing that is kind of prosperous, they're well-educated parents, they're more likely than poorer children to have experience with music and also to play soccer. They're also likely to attend good schools, get good health care, and be encouraged to study hard. These advantages lead to high test scores. Family background is a lurking variable that explains why test scores are related to experience with music. We know that correlation does not imply causation. Even very strong correlations may not correspond to a real causal relationship where X is actually the one and only thing that's causing a change in Y. I said that it's going to take our entire year to be able to come to some conclusions about causation. Correlation may be explained by a lurking variable. Okay? Here's another example. Does lack of social relationships cause people to become ill? Or maybe it's reversed. Maybe if somebody is chronically ill, that might be impacting their social relationships. Okay? These researchers found a strong correlation between those two variables, but which one might be impacting the other? And is either truly causing the other, or is there some other variable that might be implicating both? Okay? Are unhealthy people less likely to establish and maintain social relationships, or is it reversed? So, a little bit about causation, but we're going to get more into this later in the year. A properly conducted experiment may establish causation. Okay? A randomized experiment where you are controlling the treatment that the test groups are subjected to. It cannot be just an observational study where you're observing people doing things they choose to do on their own. Okay, we'll be looking at randomized experiments versus observational studies. Okay. Other considerations: we cannot do an experiment if the association is strong, or when we cannot do an experiment, I should say. The association is strong, the association is consistent. We want to see that over and over again. Higher doses are associated with stronger responses. That might indicate a better impact on our response variable. The alleged cause precedes the effect in time, and the alleged cause is a plausible, reasonable explanation. Okay? Chances are, if your results are very striking about a relationship between this thing and another thing, and you're trying to then say that this is causing that, well, if it's so off the wall that you're surprised there's a relationship, like swimming pool drownings in Nicolas Cage films, it's probably not that one thing is causing the other. Okay? It could just be a coincidence for all we know, if there isn't a lurking variable there. So with all those in mind, I have a couple quick relationships here that I just want to kind of process and make sense out of. There's a strong correlation in a northeast United States city between weekly sales of hot chocolate and weekly sales of facial tissue. You know, like this. Would you interpret that to mean that hot chocolate causes people to need facial tissues? No. There's a lurking variable out there that explain the sales of both of them. And that would just be seasonal cycles and weather. And if it's winter and it's cold, you're probably going to be selling more hot chocolate, and you're probably going to get more people needing facial tissue, running noses, people getting sick. If you're to draw a scatter plot of number of women in the workforce versus number of Christmas trees sold in the United States for each year between 1930 and the present, you'd find a very strong correlation. Okay? Why is this happening? Well, some people want to make a direct connection about like women out there in the parking lots selling Christmas trees every December. No. Okay? There's no direct relationship here. It's just, we start back in 1930, okay? You're in the Depression, okay? World War II starts, men are off fighting, women are now starting to pick up the manufacturing to support the war effort, and then women continue to be an important part of the workforce in the United States all the way up to the present day. So you get more and more women involved in the workforce in the United States up to the current day. Well, Christmas trees sold, okay? Whether that's a real tree or an artificial tree, I've had some people use that excuse before. Okay? We're talking about Christmas trees being sold. The population has increased in the United States since 1930, quite a bit. A lot of the population celebrates Christmas, so therefore more Christmas trees are being sold. There's no direct relationship. If anything, population could be a lurking variable that would explain some of both of these. Okay? More people, more women working. Okay? So don't try to connect things or combine things that shouldn't be combined. Lastly, researchers have shown that there's a positive correlation between the average fat intake and the breast cancer rate across countries. In other words, countries with higher fat intake, like the United States, tend to have higher breast cancer rates, like the United States. Does this correlation prove that dietary fat is a contributing cause of breast cancer? This is a slippery slope. Okay? You talk about like the dangers of social media and kind of perpetrating and spreading falsehoods. Okay? This is kind of something that you might see on social media, that like your great aunt Sarah or whatever comes across some evidence of, well, look at the United States and their diets and their breast cancer rate, and look at some other country. Okay, they don't have nearly the same fat intake in their diet, and they don't have anywhere near the same breast cancer rate that we do. Okay, so there's a correlation between those two, but that alone is not enough to say that it is the dietary fat intake that is causing breast cancer. I'm sorry, it's not that simple. The real world is not that cut and dry. Think about other differences. Think about other lurking variables. Okay? Other countries, if we're talking about countries that have diets much different to ours, they probably have a lot of other differences to the United States than just their diet. Okay? And part of it could be if they're very socially, economically different than the United States, they might not have the same access to health care that we do in the United States, most of us. And it could be that the breast cancer is there, it's just not being identified and being tracked. Okay, so I'm not saying that it's not true, I'm just saying that it's not that easy to say that one thing is the cause of another. It should make you suspicious when you see something like that. Okay? All right, so that's all I have here for regression and correlation. Thanks for your attention.